Is there any online questions? No, sınıftaki arkadaşların sorunuz var mı? Okay, so we will continue our review. Last time we were talking about this ideal Brayton cycle. This is a review from last year. I mean this year, but last semester. Let me get this plugged in quickly. And we talked about ideal Brayton cycle. And this Brayton cycle is the actual thermodynamic process that describes the process that that governs the operation of basically gas turbine engines. Yes. So, but what you're looking at is on the screen is the ideal Brayton cycle. However, have you seen the non-ideal cycle in propulsion? Yes, you have already seen the propulsion one. Let me get a
Yes,
pen.
we did.
So the non-ideal cycle, of course, for those of you who attended last week's class, also we had during the break, we basically went down and take a look at the engines. And you see that it has many components, and you know that in this class we will discuss these components, but these components are, let's say, they suffer from losses, okay? They are not ideal components, they suffer from losses, and these losses are not visible in this ideal Brayton cycle. Whenever we have, first of all, do you understand when I say losses, what do I mean losses? For example, let's say in a compressor, so you have, we can again walk down and we can see the actual compressors downstairs, but in a compressor, what could be generating losses, for example? What do we lose?
Total pressure.
Friction causes the losses.
Yes.
But what do we lose?
Energy.
Energy. Okay, good. We lose energy. More specifically, we lose, I can say, kinetic energy of the fluid, and also that also gets reflected the main to a main parameter that's a direct indicator of loss, which is total pressure. Okay, so. When we have a real cycle or real compressor, not an ideal compressor, of course, that because of friction, and friction is an irreversible process in physics, you know that, because of friction, some kinetic energy of the fluid, we lose it. In fact, we don't lose it, it just gets converted to what I can say, to heat, okay? So when it's converted to heat, I cannot make use of that energy, because in a jet engine I need kinetic energy of the fluid. I need that. So basically, if I lose some part of it and it's converted to heat, it's kind of useless to me. Okay. So the question is how much. Of course, since it's turning to heat, whenever I have some heat transfer process, I know that entropy will be generated. Okay. So it's an irreversible process due to friction, and friction in fluid mechanics is related to, first of all, viscous effects, boundary layers, all of that stuff that we have seen in aerodynamics too. And in a real engine, of course, we have all of this, plus we have many other complex fluid mechanic phenomena that's happening inside a compressor. So they cause losses. So, and generation of enthalpy. So if I come back to here, this line from 0 to 3, for example, is in the ideal Brayton cycle is not, I cannot maintain a straight line. I have to go from the same pressure level P0 to the same pressure level P3 through a line like this. So I'm going to exaggerate through a path like this, let's say 3 prime, okay? So that is a more realistic path. What happened in 3 prime? Well, my initial pressure is the same. Final pressure is the same. That did not change. Only thing that changes two things. First of all, 3 prime is at an increased entropy level, so reflecting the loss generation. Plus, 3 prime is at an increased temperature level. So normally an ideal compressor, let's say it's doing some, it's spending some energy to drive the fluid through the engine. So it's, let's say, spending 100 kilowatts of power. From the compressor, ideal compressor that is operating between 0 to 3, let's say a non-ideal compressor that is operating from 0 to 3 prime would be spending more power, not 100 kilowatts anymore, maybe 110 kilowatts to do the same job. And the job is to increase the pressure level of the fluid from 0 to 3. How do I know that it is actually spending more to do the same job? Because that energy spent is related to this temperature difference, yes? Our initial temperature is, let's say, 0, let's say T0. Our final temperature for the ideal compressor is 3. For the non-ideal compressor, it's 3 prime. So 3 prime temperature is higher than 3. So the power spent by the compressor or the power consumed by the compressor is just related to Cp times this delta T, right? If you remember. So the delta T for an ideal compressor is, you can see, smaller than the delta T for a real compressor. So obviously a real compressor requires more power to do the same mission or to do the same job. And again, I'm repeating, the job is to change the pressure level of the fluid. The pressure level change is the same. Is it from 0 to 3 or 0 to 3 prime? It just changed the pressure from this constant pressure line to the upper constant pressure line. So it did the same job, but unfortunately it consumed more energy. And why did it consume more energy? Because it has to spend some extra energy to those losses. It has to overcome those losses. Yes, that's the main reason. Let me turn on my camera right away, guys. Yes, so this is just specifically to compressor, explaining the difference between the ideal case and the non-ideal case. But similar arguments also occur for turbines. So in this class, when we, for example, start discussing compressors, what we are going to do is we will learn the aerodynamics of a compressor, and we will learn, for example, so here we just say, okay, there are losses in the compressor, it generated this non-ideal cycle. But where are those losses getting generated from? That's what we're going to learn in this class. Okay, so we're going to go into more details. Now, coming to turbine and nozzle. Nozzle is a little different. It's a simpler story because there's no rotating component. But let's focus slightly first on turbine, which is another rotating component. So on the right-hand side of the cycle, we see 4 to 5 process, isentropic process. As you can see, straight line coming down, no entropy is generated. So similar to compressor, we do have losses in a turbine. And mainly because of the same physical, or let's say similar physical reasons, friction, viscosity, boundary layers on the blades, boundary layers on the walls, and plus we have other stuff that's happening in a turbine. For example, we cool turbine blades. So we have some mixing of coolant flow that is being ejected from turbine blade, mixing with the main stream. So that also increases losses. Tip vortices, similar to compressors, we have all of this. So we have different loss mechanisms generating entropy. So what happens is this line cannot go from 4 to 5 as a straight line. And then let's say, by the way, 5 is there's little black line here on 5, as you can see. This is actually another pressure line. This is part of a pressure line. I can extend it like that. Okay, so I apologize for my bad drawing, but this is some kind of pressure, is intermediary pressure between P0 level and the P3 level. So this is, I don't know, let's call it, so to be consistent with here, let's call it P5 level. So now, it's not going to go through a straight line from 4 to 5, but it will go through like this line to the same pressure level. So pressure at this point and pressure at this point are equal to each other because they are sitting on the same pressure line. However, what is not equal are the entropy levels. Entropy is again increased. Plus, now the story for the turbine. First of all, what does a turbine do? A turbine produces power. Okay, a compressor consumes power, spends power. It spends power for one purpose, to pressurize the fluid. A turbine produces power. It does not consume power. So if you look at the temperature, for example, the ideal turbine has at 5 has a lower temperature compared to the non-ideal turbine. So let's say this we call this 5. Let's call this 5 prime. So T5 prime is actually higher than T5. What does this mean in terms of produced power? Because turbine, I told you that turbine is producing power, and I'm guessing that a non-ideal turbine should produce less power because of losses. Is it really like that? Yes. Again, if you do the same thing, you know, if the power produced by the turbine is equal to the Cp times delta T. Of course, I forgot to say when I was discussing compressor, you have to multiply it also by mass flow rate. M dot times Cp times delta T, right? That's the power produced by the turbine. So assuming the same mass flow rate is going through the ideal and the non-ideal turbines, the delta T for the 4 to 5 prime case is smaller, as you can see. Okay, the delta T from 4 to 5 is bigger than the delta T from 4 to 5 prime, which makes, for the given same mass flow rate and same Cp conditions, a non-ideal turbine produces less power. Okay, directly we can see it from the TS diagram. Good. So the special discussion when we are discussing ideal cycle and non-ideal cycle are especially related to these parts, compressor and partly inlet. You see down here, actually, there's an inlet part. So this is another pressure line, P2. This pressurization from 0 to 2 is actually due to inlet. It's written here. There's no rotating component, but we can also discuss that an inlet can operate as an ideal or non-ideal. We already discussed compressor, ideal or non-ideal. Turbine can operate ideal or non-ideal, and also nozzle from 5 to 8 in this case, in this plot, can also be ideal or non-ideal. Inlet and nozzle are non-rotating components, but they can, I mean, since these are basically simple duct, I'm not simple, but they have spatial geometry ducts, basically. Those ducts have boundary layers on their walls, and due to viscous effects and friction. So in the presence of those viscous effects, basically inlets also lose some, also cause kinetic energy loss from the fluid motion. Therefore, total pressure gets lost. So inlet and nozzles can also be ideal or non-ideal. So when we compare ideal Brayton cycle with non-ideal Brayton cycle, those are the main components that we are interested in, because combustor itself is entropy generator anyway. When we have heat transfer in the combustion chamber happening through this chemical reaction, entropy is generated anyway. So we cannot really talk about an ideal combustor or a non-ideal combustor. It's irrelevant. However, there's only one thing about combustors is that, and I need to clean all of this up. Can I clean that? I don't know how to do that. Erase all ink. That's good. In the combustor, there's one issue. Of course, entropy is generated, that's fine. But as you can see in the ideal Brayton cycle, during the combustion process, we go from 3 to 4 on a constant pressure line. So we are basically assuming that pressure and especially total pressure is not going to change inside the combustor. That is not true. That is not true. In reality, and if you remember, I mean, some of you have seen the actual combustors down in our hall in the department. But for those who are attending this week, you can also go down. You see the combustor geometry is quite complicated. It's not just a simple duct. It has holes around it, and those holes generate penetrating jets, air jets that is being filled, that kind of fills high-speed air jets into the combustion chamber. Those high-speed air jets collide with each other. Plus, on top of that very complex flow region, we inject fuel droplets. Okay, so it's very complex flow environment that also generates some pressure loss. At the end of the day, the reflection on this cycle is that at 4, we cannot maintain the same total pressure. At 4, in reality, in a non-ideal brightness cycle, we operate at a slightly reduced pressure level. So 4 is actually, let's say this is 4 prime, is actually here. So even if you reach ideally to 3, let's say the path will go like that to 4 prime. So you will lose some pressure inside the combustor as well. So combining all of this, again, let me clear up the slide. Combining all of this, a non-ideal cycle, if I now combine everything, it will be some kind of, let's say, non-isentropic compression to P3 level, and then some kind of pressure loss, including in the combustor, and then basically I will just draw it continuously, some kind of non-isentropic expansion through the turbine and the nozzle. So that now is a more realistic case, which we call the non-ideal brightness cycle. Now, when we compare, of course, ideal engine does not exist. We know that in real life, it does not exist. But it is an excellent reference case for us. We can compare every single real engine that we built to the ideal case. Compare its performance, compare the performance of the real engine with the ideal engine, yes? So when we do that, we can, of course, do this comparison component-wise. We can compare real compressor with ideal compressor, real turbine with ideal turbine. And then that comparison we can actually quantify it. We can come up with some numerical value. We call those numerical values efficiencies, isentropic efficiencies to be more specific, yes? So isentropic efficiency, so when we say a compressor isentropic efficiency, it's just the ratio of, and remembering that compressors consume power, it's just the ratio of how much actually would an ideal compressor consume in terms of power compared to how much power consumption does an actual compressor have. And I know that actual compressor will consume more power. So in an efficiency definition, efficiency generally changes between 0 and 1, always, not generally, always. So this means that the ratio, for example, for the compressor efficiency, beta C, let's call it, will be the power consumption of an ideal compressor divided by the power consumption of a real compressor. This is how we define it. And power consumption of ideal is less. We just discussed it in this class. Discussion related to CP times delta T's and everything. So this is how we define compressor efficiencies. We can do this to other components as well, for the inlet, for the nozzle, for the turbine. For the turbine, let's also write this down, eta T, let's say. Now, turbine is not a compressor. The turbine does not consume power, it produces power, right? So now we have to compare that fact, meaning that how much would an ideal turbine can produce power under the same conditions compared to a real turbine, how much it can produce. Okay, and I know that an ideal turbine would produce more power. So in that case, ideal power production should be down here in the equation. And the actual or real power production is here at the top of the equation. So don't get confused. Look at here, this and this definition. In one case, ideal is at the top of the equation. In one case, ideal is at the bottom of the equation. But the reason behind this, I just explained. Because one of them, a turbine, produces power, compressor consumes power. Yes? And if you remember again from last week, and you can actually play with it yourselves downstairs, they sit on the same shaft. One end of the shaft, we have compressor, other end of the shaft, we have turbine. So whatever turbine is producing, the compressor automatically gets consumes that. So they have to match. We will discuss this. How can we make sure that they actually match turbine design and compressor design? But that's toward the end of the semester. So regarding this ideal versus non-ideal cycle and everything, these component efficiencies are very critical and they do show up in the performance equations. So when I say performance, again, as a review from last year, performance of the turbojet engine depends on all of these parameters, but maybe I should show this one first. Let's remember this one first. The thrust equation, okay? Again, I'm assuming that you have seen this in propulsion one. Thrust equation for a simple turbojet looks like this. There are many parameters. I think you actually derive this equation in propulsion one, but it's a function of first m dot a. M dot a is the air mass flow that goes through the engine. Okay, and it is directly related to the size of the engine. If you remember, we discussed this also last week. Plus, there's a parameter called F. F is what we call the fuel to air ratio. Again, just to remind you, F is just m dot fuel divided by m dot air. Okay, it's called fuel to air ratio. Jet exit velocity, so UE is the actual, whatever jet exit you have at the exit of the engine. U is your, let's say, free stream velocity before the engine. But of course, this free stream velocity will be different. For example, if you are talking about a passenger aircraft, most of the time engines are under the wings. So they are exposed directly to flight conditions, flight velocity and Mach number. If you're talking about a fighter aircraft or a missile type of configuration, these are most of the time embedded inside the fuselage. So they are not exposed to direct flight conditions due to different reasons, and we will see that. So therefore, if they are embedded inside the fuselage, the question is, what is the actual Mach number in front of the engine inside the fuselage? That's what we would like to know. But anyway, we will discuss this. And currently we are kind of simplifying it. So we think that we think this as it's the flight velocity. Nozzle exit area is in the equation, AE, so the actual area of this nozzle is important, as you can see. PE is the actual static pressure of the fluid at this plane. exit pressure is important. And atmospheric pressure, so outside the engine in the atmosphere, where you are issuing this high-speed jet, what is the atmospheric pressure? And you know that this is a function of altitude, okay? This changes with altitude. Sea level is different, 10 kilometers is different. So we need to know the altitude to know PA, and of course, you also has Mach number information, is related to flight Mach number. Flight Mach number is related to also ambient temperature, because speed of sound depends on ambient temperature. So your flight conditions, meaning how fast you're flying and how high you're flying, therefore directly appears in the thrust equation. Okay, so this was the general, let's say, performance indicator of the engine. Starting from here, from this equation, you can, for example, derive T over m dot A, which we discussed last week. We called it specific thrust. Again, starting from here, we can, from a performance analysis point of view, you can derive an equation for m dot fuel over thrust, which we call the thrust specific fuel consumption, TSFC. So these two main performance indicators of a jet engine, specific thrust and TSFC. Okay, so what is hidden in this equation is actually in this slide. Okay, again, you have seen these details, I believe, in propulsion 1. Now, if you go to, if you detail this equation a little bit more, now we see these parameters. We see parameters related to components. First of all, efficiencies. Let me go over these points quickly, then we will give a break. Efficiencies, all of them are here. Yes. And the compressor, turbine, diffuser, nozzle, everything is here. Compressor pressure ratio. Now that is interesting. We say P03 or P02. So generally, if you remember the station numbering on a jet engine, just in front of the compressor, it's station 2. Exit of the compressor, station 3. So stagnation pressure ratio or total pressure ratio 3 to 2 is what we call compressor pressure ratio. And it does show up in those performance equations, if you work out the equations in more detail. Similarly, turbine inlet temperature, so just exit of the compressor, I'm sorry, combustor is station 4. Turbine inlet temperature is, it shows up. We have fuel injection here, so Q is occurring here. So therefore, what kind of fuel do we use? What kind of hydrocarbon fuel? Or do you use hydrogen or whatever? What are you using? The heating value of the fuel shows up in the equations. We have already talked about the flight Mach number, already talked about the flight conditions, and of course, gas properties, all these CPs, gamma values, R values that we see in our equations, they do change with temperature. They are not constant. I mean, we tell you, since you are only third-year students and very young, with last semester we told you maybe use them as constants. Now you are more mature, so we say that, okay, you cannot do that anymore. These are actually, all of them are functions of local temperature, and temperature change across the engine, throughout the engine. So these need to be calculated. Anyway, so again, all of these parameters, now component parameters, they directly appear in a more, let's say, refined version of this equation. So anything that you play with here, if you change your compressor, so therefore pressure ratio will be different. If you, let's say, play with your fuel type, play with your injectors, play with your combustor design, T04 will be changed. So anything that you change will have a direct impact on the performance, specific thrust, and the thrust specific fuel consumption of the engine. Okay. Okay, so let's stop here for 17 minutes. online and offline, and let's meet again in 11:40. Okay, everybody over there in the online class. We'll meet again in 11:40. Evet, merhaba tekrar. Online'daki arkadaşlar, sesim geliyor mu?
Evet
Geliyor
hocam.
hocam.
Tamamdır.
Hocam, I have a question.
Go ahead.
In Prop 1 course, we have always investigated the cases with the trust formulation. The second term was always comparably small compared to the first term. Is there an application or situation that the second term becomes comparable?
Second term meaning that this
Pressure
AE
difference.
pressure difference term.
Yes.
Okay, let me explain it like this. Under, let's say, idealized operating condition, generally we try to keep this exit pressure to atmospheric pressure, close to atmospheric pressure, or if it's equal, or try to make it equal. Then that term, yes, it does become much smaller to compare to the first term. Okay. But of course, this completely depends on exit pressure of the nozzle. Exit pressure of the nozzle is determined by the flow conditions inside. If you remember from the aerodynamics 2 class, for example, when we discuss this, for example, converging diverging nozzle, right? There were certain situations where PE can be higher than P atmospheric or lower than P atmospheric, and that causes, and we will see again those in this class, but that causes what we call under-expanded nozzles, over-expanded nozzles. Do you remember those topics?
Yes, hocam.
So yes, if those are the cases, meaning the nozzle exit pressure is not exactly matched to the atmospheric pressure, that will create some strange flow patterns and that will reduce your performance. But generally, especially if you have a variable geometry nozzle, so some mechanical system to change, for example, nozzle exit area, AE, or sometimes nozzle throat area, then you, under different flight conditions, for example, your aircraft could be flying at different altitudes, you can still try to match exit pressure, which makes the second term small compared to the first term. Tamam, Sadık. Kim sormuştu? Sadık Sefa.
Thank you hocam.
Sadık, tamam.
Evet.
Okay, so so let's continue. Okay, before I continue, let me make one more comment. If I can go back to this slide. Now, okay, so basically, all of these parameters, yes, they do appear in the performance equation, but now the question is, let's say, you know, I did some non-ideal cycle analysis for an engine. And that non-ideal cycle analysis gives me some thrust or some specific thrust, some thrust-specific fuel consumption. And let's say those values actually satisfy my requirements. Okay, so that's the first step in actual engine design. The second step is the cycle analysis tells you in order to achieve that performance, that engine should use, for example, a compressor that will have this pressure ratio. The question is, how are you going to design a compressor now which makes sure that it generates this pressure ratio under different operating conditions? Okay. Is it going to be an axial compressor, a centrifugal compressor? How many blades will it have? How many stages will it have? We will define all of these later. Okay. So now the second, let's say, level of design is to design this compressor that will match that cycle analysis. Okay, so in terms of pressure ratio. also that compressor will require certain amount of power. That power will be supplied by the turbine. So this means that the turbine will have to be designed specifically to provide that amount of power. Yes. So how many stages of turbine should I design? How many blades, rotor stator blades, will the turbine should have? Yes. So now we have to determine. So basically, this what you have learned so far in propulsion 1, and partly we are reviewing it propulsion 2, is the starting, let's say, process that we use in engine design: ideal cycle analysis and non-ideal cycle analysis. That defines our engine operation envelope, basically. And then we go into component design. And the components must be designed, again, I'm repeating, to ensure this performance that we obtained from the cycle analysis. Okay. And of course, above cycle analysis, what do we have? We have the performance of the aircraft. Okay, this aircraft could be anything, as we have seen many different examples last week. It could be anything. It could be, a supersonic missile, or it could be, low subsonic aircraft. Depending on whatever we need, the aircraft actually has certain needs or requirements in terms of its propulsion system. Those are reflected first into the cycle analysis, and then to the component design of the engine. So again, just to remind you, few performance related issues. What you're looking at here is the performance of the turbojet. We have two y-axes here. On the left y-axis, we have specific thrust. So here we have specific thrust. On the right y-axis, we have thrust specific fuel consumption, m.f/t. And on the x-axis, we have compressor pressure ratio. Okay. So the top curves, so these three curves are for the specific fuel consumption, and these three curves are for the specific thrust on the left y-axis. And for a given compressor pressure ratio, you can see a certain flight condition. In this case, we are at what we call static conditions. So actually, we are on the runway, for example, or more realistically, we are in takeoff condition. Takeoff condition occurs at very low speed and very low Mach number. So it's not maybe exactly zero, but it's very close to zero. Yes. So in that condition, let's say given a compressor pressure ratio, let's say 20. So we have a straight line here marked at 20. If your compressor pressure ratio is fixed, okay, let me first explain before going there this. For a given maximum temperature inside your engine, so the maximum temperature occurs at the turbine inlet, yes, at the exit of the combustor. And this is in reality known as a technology parameter, because normally the higher the turbine inlet temperature, the higher the performance. However, it's very much limited by materials capability, cooling capability of your turbines, manufacturing capability of your turbine blades, in terms of casting, single crystal casting, or whatever. So this is very much called technology parameter. And we see three curves, each one for a different turbine inlet temperature: 1700, 1600, and 1500. So for any of them, if you choose any of them, as you keep increasing compressor pressure ratio, as you travel along the curve, the specific thrust increases, as you can see. In fact, it increases up to a certain level of compressor pressure ratio. If you increase this compressor pressure ratio even further, the performance drops actually. So there is kind of an optimum value, okay? There's an optimum value. So for example, in this case, it's around 20, okay? The compressor pressure ratio is around 20. We see more or less maximum values in specific thrust for more or less all temperature levels. So for any engine design, and when we are designing the compressor, this is one point that we need to calculate as engineers. What is the optimum pressure ratio for this engine? Okay, for this compressor, I cannot select any compressor pressure ratio. Now, and this is in the static condition, by the way. We will see what happens if it's not static condition. Regarding fuel consumption continuously decreases as you keep increasing compressor pressure ratio. So it's good. There's no optimum, so the higher the better. Fuel consumption says the higher the compressor pressure ratio, the less fuel consumption will it be. Of course, it will be, but it changes based on the turbine inlet temperature levels, of course. Higher turbine inlet temperature requires higher fuel consumption, or you can argue the other way around. Higher fuel consumption also generates, let's say, a higher turbine inlet temperature. But in any case, higher compressor pressure ratio, if you go to the right on this axis, you see that fuel consumption goes down. So therefore, yes, we want that. We want, let's say, smaller fuel consumption, especially if you're dealing with civil aviation, passenger aircraft, that is. For military aircraft, it's not our priority. Our priority is more, let's say, thrust generation, performance, and all that, not fuel consumption in military design. But for civil aviation, of course, it's the top priority. But so therefore, this shows you, you can, I mean, designing compressor is not that straightforward. I mean, you cannot, first of all, select any pressure ratio and your compressor, and you know that aircraft is not going to fly all the time at design conditions, especially if you're dealing with a military system. For passenger aircraft, let's say an Airbus or a Boeing passenger aircraft, yes, it does spend most of its life around its design condition. Cruise flight, yes? Maybe, of course, except from takeoff, landing, and maybe some, slight maneuvering. Other than that, most of its time, design condition. So compressor, which means that aircraft is at its design condition, certain flight Mach number, altitude. Engine will also operate its design condition, meaning compressor pressure ratios, turbine inlet temperatures, turbine pressure ratios, everything will be very close to design condition. This is not at all the case for military systems. A fighter aircraft can do anything, basically. Any altitude, any crazy maneuver, it has to be able to do that. So this means that it's a little bit more difficult to design those military engines. But in any case, you see the impact of just one component here. Just we are talking about compressor pressure ratio. There are other components, there are other parameters, impact on the overall performance. And this in reality also changes if you start flying at high speeds. General characteristic is the same, meaning that again, at a Mach number of 0.85, so now you're flying at a reasonably high Mach number, almost in the transonic regime even. Fuel consumption again drops down with compressor pressure ratio. And there is again an optimum for specific thrusts, so that those trends did not change, only the levels changed. If you consider, for example, for the same compressor pressure ratio of 20, let's say if you're flying at Mach 0.85, this engine consumes around 0.03. If I go back to the previous slide, 20 and let's say Mach 0, you're somewhere here, so it's a little bit different. So it actually changes the fuel consumption level. Also, the specific thrust level is around maybe 1.1. If I go back here, this is less than 1. So specific thrust level is also a little bit different. So now this indicates not the a second parameter, not only compressor, one of the components, compressor pressure ratio in this case, but also flight conditions, they do affect the engine performance as well. If you go to higher and higher Mach numbers, Mach 2, Mach 3, of course, we go to very, let's say, of course, without an inlet. This is just thinking that we do not have an inlet. Compressor inlet is actual Mach 2, which is not realistic in reality. We have to have supersonic intake design and everything, but that, we will see that story later. But in any case, if you go to higher and higher Mach numbers, this turbojet engine, this is still turbojet engine, all that equations that we have seen, its performance drops drastically, which should give you the message: don't use a turbojet if you want to fly this high, this Mach numbers. Okay, use something else. What is that something else? If you remember last week, we have seen, I show you some plots. For example, ramjet is a better option in that case. Yes. Just quickly, regarding the turbine inlet temperature, development, historical development. So the x-axis is years from 1940s to 2020s, and the y-axis the turbine inlet temperature or turbine entry temperature in Kelvin. So back in 1940s and 50s, we are talking about the first or second generation turbojet engines, and I've shown you some examples of aircraft like the ME-262 first jet engine fighter aircraft, the F-4s, F-104s. In those engines, we have our turbine inlet temperature levels was around 1,100 Kelvin or so. Okay, it was quite low compared to today. For example, here in 2010, 2020, we have around 2,000 Kelvin. Okay. Of course, it makes a big difference in engine performance, but we achieve this through introduction of a variety of different technology levels. Cooling is one of them. Here we have uncooled and cooled versions. Green squares are uncooled. For example, in 1960, we have an uncooled engine compared to a cooled engine. You can see we can increase the temperature level almost close to 200 degrees Kelvin. Okay, and the cooling technology, of course, it's a big research field. Still a big research field. It started in 1940s, so after almost 80 years later, it's still a big technology and research field. In addition to cooling, the materials, certain high technology alloys are used in turbine blades. You cannot use aluminum, you cannot use steel, very high technology nickel-based alloys that you need to use. And in terms of manufacturing, you cannot, generally you don't do, CNC machining or anything like that. These are produced by casting, döküm. Okay, but I guess you have all taken by this point in your lives a materials class, casting. Maybe you might remember. The problem with casting is this: when you cast a metal and it starts cooling down, it creates what we call grain boundaries when it's cooling. Okay, when you take a look at a microscope and take a look at the metal structure, it's like blobs of metal attached together with some with boundaries. Those are called grain boundaries. This is something we do not want, because these grain boundaries are very susceptible to mechanical failure, the crack starting and crack propagation. So the question is, can we actually cast a turbine blade which works in a very harsh environment, very high temperature and very high centrifugal loads, because these are rotating at high RPMs? Can we actually cast without any grain boundaries? That special casting process is called single crystal casting. So this entire blade, and it's been done for some years now, but it's very critical technology if you want to design an engine. For example, in Turkey, we did not have single crystal casting technology, but I think it's developing slowly, because especially if you want to design the hot part of the engine, turbines, you definitely need to have single crystal casting technology. Nobody will sell this technology to you even if you pay for it. Okay? It's very proprietary technology. So now they cast the whole turbine blade like this big. It is the entire blade is one crystal, meaning one grain. There is no grain bound. So it's very much resistant to cracks, very much resistant to mechanical failure and thermal failure. So single crystal cast alloys and thermal barrier coatings started to appear in the 1990s, as you can see from here. And then engine performance increased quite a bit. So, but in terms of material design and thermal design, we will not go into too much detail in this class. We will mostly go into, let's say, performance and aerodynamic design of turbines. Okay. Now, just a quick recap of, what I call spin-offs of turbojet engine technology. One of them is the turbofan. Yes, a turbofan engine is what you're seeing here, and of course the thrust equation is basically the same. You don't see the second term, by the way. It's only the first, first few terms, not the pressure difference term. The design philosophy of a turbofan engine is different. Okay, again, recapping from last semester's propulsion class. The design philosophy is different. The design philosophy of a turbojet is to generate high-speed jet at the exit, UE, high UE. The design philosophy of a turbofan is not that. The design philosophy of the turbofan is, I'm going to generate the same amount of thrust with low UE. Okay, then the question is, if the UE is low, how are you going to generate the thrust? Well, UE is not your only option. In the equation, we have another very strong option. That second option is m.a. Here, m.a. You can keep UE minus U low, but if you have a high enough m.a, you can still generate the same amount of thrust. Okay, so that is the design philosophy of the turbofan engine. So basically what we do, how do we achieve this? What we do is this, the core of the turbofan is like a turbojet. So we have a compressor here, we have a combustion chamber, actually this whole thing is a compressor. And we have a combustion chamber here, and we have a turbine driving the compressor. Normally, what do we do in a turbojet? At the exit of the turbine, we still have high enthalpy fluid. And then we accelerate it into the nozzle, and get high UE. Here, we don't do that. Here, we have that energy at the exit of the turbine. We put another turbine, a second turbine, which is mechanically independent from the first turbine. It's not touching it. It's not on the same shaft. Only thing that is connecting is the airflow. Okay, so basically with the second turbine, we extract that energy. Okay, what do we do with that energy? The second turbine now drives a fan in the front. Why do I do that? Because a big fan with large diameter ensures that I have large mass flow, m.air. Because m.air, if you remember again from last week, rho times U times area. So if you generate a large area, pi diameter square over 4 in the front of the engine, big air consumption will generate large m.a and large thrust. But of course, for that, in order to drive that large fan, you need power, lots of power. So how do you generate that power? With that second turbine, which is generally called, as also known as the low pressure turbine, in a turbofan engine. Does the second turbine extract the entire energy? No. There's still a leftover energy after the second turbine that exits as the UE from the engine. This is our equation, but if you remember from propulsion, one class, we analyzed turbofan engine separately, the core flow and I can call it hot flow and the cold flow. Cold flow is this flow through the fan basically. Hot flow is the flow through the core of the engine where you have combustion, and we call it hot flow path. So therefore, this is the main philosophy of turbofan. And in terms of its propulsive efficiency, as you can see, is much higher for turbofan. Why? Because if you remember, I do not have it here, but propulsive efficiency equation, as it's actually plotted here, it reaches a maximum, like also theoretical maximum, like 1, when U0 over UE is actually equal to 1. So when this term actually comes close to 0, your propulsive efficiency actually goes to the highest. Okay, well, this is again another thing behind the design philosophy of turbofan engines. We try to keep this term, this delta term, UE minus U. If you ignore F is small number compared to 1. Let's ignore it, so it will become UE minus U. So that delta velocity difference, if you can make it small enough, but basically try to achieve a big mass flow rate, then your propulsive efficiency is also going to be high. So there's also another big advantage of turbofan engines is that low U exit means low noise, because noise generated by an engine is proportional to this exit velocity to the power 6 or 7. Okay, so any small reduction in exit velocity will reduce the engine noise quite a bit. And this is actually what happened. Turbojet engines were being used in passenger aircraft until 1970s. Because it was invented in 1940s, applied in military aircraft. After the World War II, everybody started to use them in passenger aircraft. But it took 20 plus years to realize that, okay, nice. I mean, we use turbojet engines, we fly fast, passengers travel fast from one place to the other. But the problem is aircraft are so noisy, plus they consume crazy amounts of fuel. Okay. And in 1970s, there was a big oil crisis. And that kind of pushed all engine makers, engine manufacturers to design better engines. Less noise, less fuel consumption. The result was the turbofan engine. And today, every single commercial aircraft uses turbofan engine. Nobody uses turbojet engines anymore. Even there are certain variations of new generation turbofans, like you might have heard geared turbofan, for example. That's a new concept, relatively new, let's say. Geared turbofan, that's a new turbofan. So, but mainly analysis is very similar. So, yes, an important concept, again, just to remind you from last year, is the bypass ratio in a turbofan engine. It's the amount of cold air mass flow. Cold is the blue streamlines that you see here, compared with the amount of hot air mass flow. Those are the red streamlines in this animation. What is a typical bypass ratio? Do you have any idea? Do you remember? For this engine, for example. This is a GE90 typical passenger type turbofan engine.
7 or 8. 7 or 8, yes.
7 or 8, it could be 7 or 8. 5, 6, 7, 8, those are typical numbers. These are what we call high bypass ratio turbofan engines. Beta is what we call high bypass ratio. So which indicates that there is also a category of what we call low bypass ratio turbofan engines. Okay, and those are, I will skip those. Those are more military type turbofan engines. And one example is on your screen right now. This is the F110, GE F110 engine. This is the engine of the F-16 aircraft. And similar engines built by Pratt & Whitney are used in F-15 aircraft and also in F-35 and F-22. Those are all low bypass ratio turbofan engines. When I say now low bypass ratio, what is a typical number? Any ideas?
2, 3
Online
maybe.
ideas or offline ideas?
Hocam 2, 3 maybe.
Kaç?
2 veya 3.
Yok, çok da yüksek. İn.
Bir civarında mı hocam?
İn.
1,5.
0.5.
Çok düşük oldu. Sınıfta somebody say 1/5, that's too low. Çık.
0.5.
0.7, 0.8, 0.9. So less than 1 actually. Yeah. So those are called low bypass ratio engines, but I guess in my older slides, I actually had technical specifications of these engines, but in these slides I do not have. But you can check. This is the F100 PW229 engine. By the way, this engine is also, just as a side information, it's also used in some unmanned combat air vehicles as well, not only on manned fighter. But for the F-16, I forgot the bypass ratio, 0.8 or 0.9. It could be 0.8 or 0.9, if I remember correctly. You can check. So, but again, I mean, these engines are also turbofans. I mean, the cycle analysis, the performance analysis, all the same equations. Only thing is that the diameter is not as big as a passenger aircraft, but there's a cold flow path. You can see, I'm trying to mark on the screen. This is the cold flow path, and this is the hot flow path. Okay, so you have hot, m.a hot here, and m.a cold here, and then unlike a passenger aircraft, we mix them before we release this jet into the atmosphere. We mix them here inside the nozzle. That also helps a little bit in terms of fighter engines, because this is relatively colder airflow. This is relatively high temperature airflow. When we mix them at the exit, we reduce the temperature signature of the aircraft. Okay, this is important because you know, your enemy could be attacking this aircraft with an infrared missile. Infrared missile searches for this temperature signature. Okay, so if you mix it and reduce the temperature signature a little bit by using a low bypass ratio turbofan, also helps a little bit in terms of this thermal detectability, let's say. So okay, so one more. If we go one more step, we come again to remind you the turboprop. Inside of the turboprop, exactly like a turbojet, compressor, combustor, turbine. It's very similar to turbofan. First of all, in a turboprop, again, the design philosophy is not generating a high-speed jet. No. We put a second turbine also at the exit of the first turbine and extract again energy. But this time we are not driving a fan, but we drive a propeller in the front. Okay. Now turboprops have advantages. If you remember the plot that I showed you last week, at let's say relatively low flight Mach numbers, 0.4 to 0.5, it's more advantageous to use a prop instead of a fan. So here, this engine, gas turbine engine technology, second turbine drives a propeller in the front. So it's basically a propeller-driven aircraft, but this, since it's not driven by an internal combustion engine, the RPM levels and aerodynamics is a little bit different, but it allows you, it gives you enough power, propeller power, to fly it high enough Mach numbers. The exit velocity is almost, I mean, it's very, very low. It may not be zero, but it's very low. This is not a jet-powered aircraft, okay? It's very low. So which means that the second turbine generally is called the power turbine, extracts almost all of the energy, leftover enthalpy after the first turbine, almost all of it. But in a turboprop aircraft, there is an optimization process. I don't know if you have seen it in propulsion one, but if it, you know, leaving some U exit, not making it exactly equal to zero, but some U exit, there's an optimum level to that. You don't want to make it exactly zero. Okay, so turboprop aircraft is a special design. The best example is this ae435 military transport aircraft. You know, this Tusaj and TEI participated in this project for a long time, and they are producing their parts of their engines and of the fuselage. And Turkish Air Force is also using this. Turkey was a part of this project. So this uses the TP400 turboprop engine. You see it's an air-breathing gas turbine engine. So here you see the air inlet. Air goes in from here. Exhaust is somewhere at the back, low speed, but very specially designed propellers. You can see these propeller blades. They do not look like your, for example, Cessna aircraft propeller blades. Yes, these are advanced transonic propellers. You can see they are swept back like a transonic wing, okay, to manage the shock waves that are occurring. So their RPMs are quite fast compared to your regular propellers. A similar engine to these turboprop is the turboshaft, which we use for helicopters. We have two turboshaft engines at the entrance. One of them is Rolls-Royce 250, C250, and the other is the T700. The T700, GE T700 engine powers this aircraft, the helicopter, the Black Hawk helicopter. And it's just downstairs. We can talk about it maybe after the class a little bit, also for those of you who are in the class today. This is the Attack helicopter. Attack uses two T800 engines. It's a little bit more advanced version of the T700, very small, very powerful engines. But the internal, let's say, cycle and internal design is like a turbojet. It looks a little bit different because our compressors are not axial compressors most of the time. For example, in this one, in this engine, we see a radial compressor, two-stage radial compressor, driven by this axial turbine, and we have a combustion chamber in between, embedded here. And after the first turbine, this blue shaft is basically hosting the compressor and the turbine. And after that, we have the orange shaft, which kind of has the second turbine, similar to turbofan, similar to turboprop, but this turbine now extracts almost the power entirely. There's no optimization or anything at all for the U exit. U exit is practically zero. Okay, I mean, if you look at the exhaust of a helicopter, it's just like your car exhaust, like very hot gas slowly coming out. It's because this second turbine extracts almost all available power in the gas and uses that power for good purpose to drive the main rotor and the tail rotor of the helicopter. Yes, and in some turbo, this is called therefore the turbo shaft engine. It produces shaft power. In some turbo shaft engines, we have hybrid compressors, for example, axial and radial, and those are what we have downstairs in the hallway in aero department. Okay, so but again, the geometry is, in terms of cycle analysis, not different than what we do for a turbojet. However, in terms of component design, for this engine, you need to design a radial compressor, which is quite different than designing an axial compressor. So that's why we're going to learn this in this class. Axial compressors, we have the axial compressor subject, we have the radial compressor subject, and we will see the differences in terms of flow physics and all that. The rest of the slides are a little bit irrelevant, so let me skip quickly. Those are mostly ramjets, scramjets, some examples from literature, from missiles, ramjets, manned aircraft, some crazy manned design. And this is the scramjet hypersonic for hypersonic speeds. Let me pass through. And a hybrid engine, for example, for the SR-71 Blackbird, it's a turbojet and a ramjet. You know, this is the fastest flying aircraft, Mach 3.5 manned aircraft, Mach 3.5, and also rocket engines a little bit out of the context of this class. But some, like the nozzle design and everything, are applicable. We will talk about these. And electric propulsion towards the end of the semester. And do you recognize this vehicle?
Yes.
What is it? Yes.
The Enterprise, I guess.
The Enterprise. What kind of
Yes.
engine does the Enterprise have?
I don't know.
You don't know? Who knows? Nobody knows.
Ion thrusters maybe.
Ion thrusters. Enterprise is, you know, it's a future ship, so it has better technology than ion thrusters. It's a good
Warp
guess,
engines.
though. Huh?
Warp engines.
Warp engines, yes. It has warp drive, which is not existent and out of the context of this class. Any questions? Class or online? Okay, so let's stop here at this point. Continue on next week's class because we don't have any class on Thursday. Oldu, görüşmek üzere.
İyi günler hocam. Dikkat edin kendinize.
İyi günler.
İyi günler.
Güzel hocam.
İyi günler.
İyi günler.